Okay, so welcome to the weekly colloquium in the School of Astrophysics. We are very glad to have Dr. Pratyusha Boral as our speaker today. Like many of our previous speakers, Pratyusha did his undergrad from the physics department of Presidency University from 2015 to 2018, and then stayed back to do his master's in the same department. And Professor was an excellent student and did a lot of research during his BSc and MSc days. I think he has a couple of papers that he published with faculty members in the physics department, Dr. Ratna Kole, and some of our external members like Professor Parthasarathi Majumdar. And then Pratyusha actually, because one reason was that he was working with Dr. Ratna Kole and PSM sir, who are both experts on gravity. So he got motivated to work on gravity. And we had a GW school in 2016 where people from Caltech and people who recently joined TIFR from Northwestern, etc., they came and gave lectures. And so maybe that also played a part in Pratyusha. Also, I mean, gravitational wave was detected.
Right. When they
just before
first year, when they were just first year.
So for the first time, GW was detected when Pratyusha just joined BSc.
Yeah.
So with all these things, Pratyusha decided to work on gravitational waves in his PhD and went to one of the best departments that does this work, which is the University of Wisconsin-Milwaukee. So he has just finished his PhD and is about to join the Jet Propulsion Laboratory within the Caltech campus. And whatever my preference for Northeastern United States might be, I mean, it is one of the best or maybe the best place to work on such physics. So we are hoping a lot of good work will come from Pratyusha as well. Usually we thank the speaker at the end of the talk, which we will, but we also thank Pratyusha for bringing us snacks.
So I think this is the first time in the history of colloquium that the colloquium speakers themselves got like this bag of snacks for all the audience. So
it may be, yeah. It may be a carryover from the thought that at least in some places, when the PhD student is defending their thesis, they bring snacks for the audience. So, for example, I did for my PhD thesis defense. So anyway, thank you, Pratyusha, and we are very curious to hear from you.
Okay, so thank you, RC sir, for the very kind introduction, and also thank you to SC ma'am, SS sir, for inviting me to give this colloquium in the School of Astrophysics. So this is my first colloquium I'm giving in Presidency University, and I'm really like, when I joined Presidency University, every Wednesday there was this Presidency colloquium, and I think it was very new at that time. So I'm very happy to come back again as a colloquium speaker. I think 10 years, it's 2026, so 11 years down the line. So yeah, again, thank you for inviting me. So as Assis has said, we had our first detection in 2015, which was eventually published in 2016. And that was GW 150914. And now if you look at the latest catalog, there are 390 detections. And that catalog is GWTC 5, or the Gravitational Wave Transient Catalog. 5 means it's the 5th catalog. And the 6th catalog will be released sometime in December. So today I'm going to be talking about how do we detect these sources and why do we see these sources, why do we see these masses and stuff like that. And then I would also highlight some detections from the 4th observing run. I'll be talking about 4 events. 3 of them I chose because I worked on them, and 1 event I thought, yeah, it would be interesting. So let's get started.
Just click on it once, please.
Okay, so this is the rough outline. I'll very quickly describe what are gravitational waves, and then I'll move on to talking about how we detect these sources, and as I said, why we detect these sources, and then talk about some detections and future missions. So let's get started with gravitational waves. So gravitational waves, as most of you might know, are transverse fluctuations of space-time curvature. And like if we have electromagnetic radiation, that's described by a vector field. So we just need one charge moving in a straight line to understand it. But for gravitational waves, it's described by a rank 2 tensor field. What that means is we need a ring of particles which can get stretched or squeezed. And by measuring how much the ring of particles is stretched or squeezed, we can talk about the strength of the gravitational wave. So just quickly motivating how the gravitational wave strain looks like. So again, it's very similar to electromagnetism. If you want to take a look at the gravitational wave strain, which is denoted by this letter H, this is the change in length divided by the original length. That's the second derivative of the quadrupole tensor. The reason we need to look at the quadrupole tensor and not the monopole term or the dipole term, because the time derivative of the monopole term is conserved because mass is conserved, and same with the dipole term because momentum is conserved. So the first quantity that we can measure as gravitational waves is the change in the quadrupole tensor, and this is the and if you do a dimension analysis, you will see you would need terms like g by c to the power 4, which is a very small number. So we need massive objects to get a substantial strain that we can measure. And if we think about, okay, what's the heaviest objects that we see in our day-to-day lives, it's nothing but the sun. So the first question is, let's say we have two objects like our sun, then how would a gravitational wave look like, or can we at all detect them? So if we have massive binaries in orbits, then we can like approximate the change in quadrupole tensor as the reduced mass times the distance squared times the orbital frequency. And if you change this to gravitational wave frequency, there will be a factor of 2, but that's not important here. But the thing to note that this distance between the orbiting binaries and the frequency is related by Kepler's third law. And we can substitute Kepler's third law here, and then we get the second derivative of the quadrupole tensor as the reduced mass times g total mass, the frequency times 2/3. And the reason I have this expression here is this tells two things. At least when the objects are coming closer to each other, the frequency will increase. And then also there is this term mu times total mass to the power 2 by 3. This is a very important combination. It is Chirp mass raised to some power, and we will come back to this Chirp mass more as I talk about this. But this is like the Chirp mass is the best measurable quantity that we have from gravitational waves, and that comes here. Okay, so this is how a typical gravitational wave form looks like, and this is the waveform that we detected in 2015, GW 150914. So we have this in-spiral phase where we have two objects which are coming closer to each other. Then we have the merger phase where then these two objects merge, and then we have a ring down phase. Like when these objects merge, these objects shake a bit, which gives this region, these squiggles at the end. So this is the in-spiral part where the frequency is slightly increasing with time, then it's merging where we get the highest amplitude, and then this is the ring down phase. So coming back to the question, let's say we have two sun-like objects, and if they merge, can we detect gravitational waves? So what we can assume, let's say the total mass is around 2 solar mass, and let's assume that the gravitational wave detector is on the surface of the Earth. If it's on the surface of the Earth, then we can't measure frequencies less than 10 hertz because the surface of the Earth shakes due to seismic activity and stuff like that. And if we just plug these two numbers, we will get the distance to be 646 kilometer. And this distance is, I think, 1,000 times less than the radius of the sun. So if we have two sun-like objects and when they merge, there will be a lot of interesting electromagnetic phenomenon. But we, like the gravitational waves that it will produce will not be in the frequency that we can detect using ground-based gravitational wave observatories. So we need more compact objects to detect this, and that's why we talk about compact binary coalescences. So we can't have two suns, we can't have two white dwarfs. If we have two white dwarfs, we can detect it in LISA. That's a space-based mission. But if we want to measure things in ground-based observatories, then we need to have neutron stars and black holes, which are much more compact. Then the frequency where they merge would be much higher. And you can also calculate what the strain is. The strain is around 10 to the power minus 21. That means this shift is around 10 to the power minus 18 meters. And this is a very small shift. It's 1,000 times less than the radius of a proton. And so we measure these incredibly tiny distances. Yeah, and this, what I said is that we need compact binaries. Okay, so this is a very schematic of how a LIGO, Virgo, or Kagra detector looks like. Basically, we are doing laser interferometry, and most of you might have done this in your bachelor's with the sodium light or lasers where you change the arm length to look at fringes. And the idea is that if we have a very sensitive Michelson interferometer, and if a gravitational wave passes that interferometer, the arm length would change slightly, and the detector is calibrated such that if there is no gravitational wave, there should be no output at the detector. So it's slightly out of phase, and when there is some perturbations, then you see some light at the detector. And measuring the intensity of the light at the photodiode of the detector, we can map this to the gravitational wave strain. So this is the gravitational wave network that we have, and we need multiple gravitational wave detectors to localize and also assign significance, which I'll be talking about later in this talk. So in United States, we have two detectors, LIGO Hanford and LIGO Livingston, one Virgo detector in Europe, one detector called Kagra in Japan, and the third LIGO detector is being built in Hingoli in India, and it's expected to be operational in the next 5 years, sometime during the 5th observing run.
So, what is the color code?
Yeah, so
no, I'm not saying that. I'm saying in the map of the world, what are the blue spots and what are the white spots?
Maybe they are dry and cloud or something or no? Yeah, maybe.
I don't know.
Seismic activity. Is it related to some sort of seismic activity? No.
I'm not sure, but yeah, I'll look into it. It's a very good question. Like I have never thought about this. Like,
yeah. Brazil.
Yes.
That is the blue patch.
Yes, that's what I'm saying.
this part.
So I'm saying the deserts, and if I look at Saudi Arabia and Northern Africa, they seem like nothing is there. So I was also thinking might be vegetation.
Okay, please go ahead.
Yeah, but it's
yeah.
Interesting question. So these are the rough sensitivities that we have, and what this number means is, okay, let's say we have a 1.4 solar mass binary neutron star merger. How far in the sky can we detect it? So in the first observing run, only the LIGO detectors were operational, and we could detect things up to 80 megaparsecs. So remember, this is for binary neutron star mergers. So if you have a black hole, then you have that mass scaling. So you can detect black holes much farther. In the second observing run, the range went up to 100 megaparsecs. And in the third observing run, it went up to 140 megaparsecs. Unfortunately, for Virgo, the range was much lower because they were having issues which they're trying to fix. And Kagra In the third observing run, the range was 0.7 megaparsec. So presently, we have the fourth observing run, and the fourth observing run was broken into 3 parts. The first part is called O4A, the second part is called O4B, and the third part is called O4C. And presently, everything up to O4B is public, and that's the fifth gravitational wave transient catalog. And soon, the O4C detections would be released. Virgo joined observations in O4B. It was not observing in the first part of the fourth observing run, and its range was around 50 to 60 megaparsecs. Kagra was off for the most part of the fourth observing run, except some patches with a range of 5 to 7 megaparsecs. For detection and significance estimation, we usually use the 2 LIGO detectors and the Virgo detector. And why we so the detector is scientifically it's more challenging from an engineering point of view because it's a very no, it's not a compact detector, but the seismic noise is very high in Japan. So they are building it underground, and it's overall an engineering challenge, which, what I've heard is that they haven't, the technology haven't been solved as of now, and so they're having issues. So they were trying to test that by putting it underground, can they isolate this noise? But yeah, that didn't work out very well. And so after O4, we have a run called IR1 because for every observing run, the sensitivities change. And in O5, it's expected to be 240 to 325 megaparsecs. And it's unlikely we will reach this soon due to funding constraints and other stuff. So the next run is called IR1, which stands for Intermediate Run 1. Or you can also call it the Iguane Run 1 because the LVK collaboration is also changing to Iguane. But this is just a run that will start around, I think, August of next year with just the O4 sensitivities. And eventually, when after IR1, we expect to get O5 when the sensitivities will increase. Or sometimes people also talk about an IR2, like this very O4-like runs. Okay, so finally, I'll be talking about how we detect these sources, or how does the detection pipeline work. So to identify gravitational waves from data, we have 3 types of detection pipelines. So the first one is template bank-based match filtering searches. And these pipelines are actually the most sensitive because you have an exact model and you try to see that if you have this template in the data. There are also other minimally modeled searches where you take the data from 2 detectors and see that, okay, do they look alike or not? And if it's a gravitational wave, they should look somewhat alike. And there are also fully machine learning based searches like A-Frame, which started operating from I think from O4B, which are very interesting. But as of now, they work well for binary black hole signals because those signals are short. But if you have longer signals, they don't work very well. Like A-Frame is only sensitive to binary black holes as of now. And today I'll be talking about the GST-LOL based search pipeline. This is the pipeline that I work on, and I'll be describing how this pipeline works in the next 10 minutes or so. So this is a schematic, an artist's impression of a template bank. As the name suggests, that it's just a collection of templates, and where each point in the template bank is a template, and depending on the masses and the spins. For GST-LOL, each template is characterized by 3 numbers, the masses of the 2 objects, and 1 effective spin. And depending on the masses or spins, the templates look slightly different. Like if we have heavier masses, the templates are shorter. And if we have lighter masses, the templates are longer. So what we do in a match filtering based pipeline is we just cross correlate the template with the data. And very loosely speaking, you can think of taking a dot product of the template. Like the template is a series of numbers, the data is a series of numbers. You just take the dot product of them. Okay, so this is basically what match filtering does. We have a template, which is a pre-computed waveform, and we slide this template over the data. By sliding, what I mean is just multiplying the value of the data at every time point with the template and summing it up. And if the data and the template matches, then we will get a peak in the signal to noise ratio. And using this peak, we identify triggers. So there are some technicalities here which I'll not go into, like we need to whiten the data and template, but the basic idea is just we take the inner product. So this is how GST-Lal's template bank looks like. So the first question you need to answer is how many templates do we want in the template bank? And that's characterized by a number. So let's say if we have a signal, and depending on how dense the template bank is, the SNR will increase. Like if it's very dense, then it will be an exact match. And so the signal to noise ratio will be high. So we need to choose a match criteria. Like for GST-Lal, we choose that, okay, we will lose maximum of 3% loss in SNR, and that's how we decide how many templates to put. And I'll explain what that means. But if we choose that we would allow a 3% loss in SNR, then we have 1.8 million templates in this mass range from 1 solar mass to 200 solar mass, like the range in the black box. I'll be talking about this gray region later. Now, the problem is if we have 1.3 million templates, we can't take every template and cross-correlate with the data. Like we would need if we have infinite computational power, we can, because we can run everything parallelly, but computational power is limited. So we can't just take these 2 million templates and just do match filtering. So what we do is we go back to linear algebra. Let's say we have two very nearby templates denoted by this red star and the blue star. So if we take the inner product of this red template with itself, we will have 1. They are normalized. If we take the inner product of the blue template with itself, we will also get 1 because these templates are normalized. This is just a normalization factor. However, if we take the inner product of this red template with the blue template, we will get something like 0.8 or something. And this is that means that there is a 20% mismatch between this red template and the blue template. Now, if we have another template that's far away, then the match between the red template and the blue template is almost 0. That means these templates are somewhat orthogonal if you think that each template is a vector in a n-dimensional space. So we can actually exploit this and do a singular value decomposition to identify some basis vectors. And we actually do that to speed up our match filtering. So again, very schematically, what we do is we just group some templates that are pretty similar. Now we need pretty similar templates because if we take two templates that are very farther, very separated by a large distance, then it doesn't make sense because they are almost linearly independent to each other. So we group similar templates and slice them, and each of these is a time slice, and for every time slice we do an SVD decomposition. So if we have a set of templates and then we do a time slide, which is denoted by this number S, and for each of this time slide we can do an SVD decomposition, and we can use these basis vectors to calculate the SNR time series, and that actually speeds up our calculations by a lot. And this is how actually we filter 2 million templates. Now, this describes how the templates are grouped, and I won't go into details for this, but this is more linear algebra. Like we can just figure out, okay, what are the eigen directions in the parameters of the template bank? And it turns out that these are the eigen directions. This Psi0, Psi2, and Psi3 are the post-Newtonian Psi's. Psi0 is basically the Chirp mass. So the first direction is very close to the Chirp mass because Chirp mass is an very, as I described earlier, it's a very important parameter, and we can justify this choice just by Keplerian dynamics. And we also have this mu2 parameter, that's the orthogonal direction to mu1, and we use these two parameters to group templates. But the issue is that, okay, we can run match filtering and we can identify triggers, but identifying triggers is not enough because the ground shakes for various reasons. Like it can be something, just a train is passing or a car is moving, and if the ground shakes and there is a glitch, then we can get peaks in the SNR time series, which is not due to an astrophysical source. So we need a scheme that will help us to identify that, okay, this is an astrophysical trigger, and this is not an astrophysical trigger, and this is noise. And doing this, what we do is, we calculate a quantity, we calculate a chi-square like quantity. So what we can do is we can calculate the dot product of the template with itself, like the best match template, the template that recovers the highest SNR. And so that is called the scaled autocorrelation. It's scaled because you need to scale depending on the distance, like you can change the amplitude. And we compare that with the signal to noise ratio. That's the measured rho of t, which is the dot product of the data with the template. And if this is an astrophysical trigger, then the dot product of the data with the template should be similar to the dot product of the template with the template. And we can calculate a quantity called chi-square, so which is just the area between these two curves and squared, something like this. And by looking at the values of the chi-square, we can differentiate between a signal and the noise. However, the question is, it's very hard to say that, okay, what value of chi-square will be a signal and what value of chi-square will be noise. And for that, we need to characterize the noise background. And in the next couple of slides, I'll be describing how JSTOOL characterizes the noise background. But one very important thing here is that we live in the noise dominated region. What it means is that if we switch on a detector and start recording data, we are guaranteed to get noise. So we expect that it will be dominated by noise. So we can just collect and study the properties. Like signals are there. It's not a signal dominated regime. And that actually simplifies our life a lot. So I'll quickly skim over this slide as it's not that much important for this talk. We calculate a quantity called likelihood ratio. So this is just the probability of the trigger being of astrophysical origin divided by the probability of the trigger being noise. And there are several things that goes into calculating the likelihood ratio. First of all, what is the population model? And for the population model, we just use a Salpeter mass function, which basically says that, okay, we expect more neutron stars than black holes, like there is a slope. And then what time and phase that we can detect, like what is the condition of the detectors at that particular time. And then if it's of astrophysical origin, there are some more consistency tests that we can do, which I'm not going to be talking about today. And similarly, we have the noise hypothesis. So how likely is it for noise to generate these triggers? And that's modeled as a Poisson process. The other terms can be analytically modeled. The most important term that I'll be describing today is the noise background. And there is no way to analytically model this because this is very hard to describe analytically what will happen, and we need to measure this in real time. And measuring this is in the heart of all detection pipelines. And I'll be talking about how we measure this term in the next. So this is the difference in time between two detectors. If it's astrophysical, then okay, if you have a trigger in Livingston and Hanford, you expect a 10 millisecond gap. But if it's not, then this just can be nothing. So we just model it as a uniform distribution. Same goes for phase and stuff like that. So this is measuring the noise background. So the first approximation that we do, that the noise background on different detectors are independent. They don't depend on each other. So we can write it as a product on the observatories, and then we have to measure the noise background. So let's say we want to measure the noise background of detector 1. And as I said earlier, we assume that if we switch on the detector, we will just get noise. So what we do is during coincident time, by coincident time, I mean two detectors are operational. So let's say at this point of time, detector 1 and detector 2, both are operational. And in detector 1, we measure something with an SNR of 12. And at that time in detector 2, we measure something with an SNR of 2. So this is likely to be noise, because if this was an astrophysical signal, both these detectors should have picked it up. And so we add this to the noise background of detector 1. Similarly, if we look at the next trigger, the SNR is 16 at detector 1 and 16.5 at detector 2. So this most likely is astrophysical, and so this doesn't go to the noise background. If we look at the third trigger, so this is an SNR of 1 in detector 1 and an SNR of 9 in detector 2. So this is a noise trigger in detector 2, but we are taking the noise background of detector 1. So this doesn't go in the noise background of detector 1. And the last one, it's 87 in detector 1 and 3 in detector 2. This is most likely a glitch. Like if you get something like we have seen signals like this, but this is very unlikely. So this is how we get the noise background, and we can also calculate the chi-square and the SNR square, and then do some smoothing and stuff to get something like this. And this is how the noise background looks like. So ideally, you want to do this for every template, because the noise background for every template should vary, but that's not possible to do. We again group the templates in to 919 groups, and we calculate the noise background for each template. Now, if you have something in this region, then this is most likely a signal, because noise can't, like you don't get noise in this region. If you have something like here, then this is most likely noise. And most interesting things lie in the boundary. And this is how actually we assign significance very schematically. Like there are other terms in the likelihood ratio, but this is one of the most important terms which we measure analytically from, which we measure experimentally from the detectors. Like there is no way to analytically model how this looks like. And we can, there was some discussion around a year ago what will happen if we just have one detector operational, because then you can't do this measuring the background in coincident time because you only have one detector. Then also actually you can do this, like your sensitivity will become bad, but you can just say that, okay, we are in noise dominated regime, and if we switch on the detector, we only get noise. And then for every trigger using that noise, we can calculate the significance of that trigger. And when we get that trigger, we can just remove that trigger from the background, because that's astrophysical. And you can assign significance, but then definitely your sensitivities will go down. Yes.
So does your noise characterization improve if you have multiple detectors? And if you increase the number of detectors, would it help in creating, understanding your noise statistics or noise characterization better?
Yeah, so like when we just switch on detectors, we need to wait till this till these distributions converge. Now, if you have more detectors, like now what we do for calculating the background in Livingston, we only take triggers when Livingston and Hanford is operational. So if we have another detector that's similar to the LIGO detectors, then we can just use that detector. Like if LIGO India has a similar range, then we can also use that detector. Then you are getting twice more data, and you're getting twice more noise triggers. So these histograms will be much more stable. For Virgo, we use Hanford and Livingston. That's why Virgo converges pretty quickly, and also its sensitivity is not good, but Livingston and Hanford takes a long time to converge. And also things fluctuate. So one, related to what you said, one important thing to note here is this background will change with time. Like if it's convergent, it should be roughly similar, but as we collect more and more data, there are tiny fluctuations. So things that are significant today can become insignificant after 6 months. And the other thing is also true. And I'll be talking about one such event called S240813D. So this was an astrophysically interesting event, and for astrophysically interesting events, like the idea is like people try to get this special events paper out within 1 year of detection. But the problem is in 1 year, we don't get the final significances because for that we have 18 months from the end of the detection. So when people start writing this special events paper, so people who work in detection, so we have to check that, okay, will this survive the final catalog? Because it would look like this can happen that, okay, this today this is significant, but when we write the catalog, this becomes insignificant, but it looks a bit bad, and it also creates more confusion in the community that if something like that is sent out. So the plan was to write a special events paper using S240813D, but it turns out, as I'll explain why, that this was found to be consistent with noise. So we had to drop the plan. So, yeah.
Map changes with time. That I understand that it might have something to do with detector and all those things. But for a particular time, how can it change? How can it vary? Means this signal you have obtained for this particular source at particular time. That time this signal to noise ratio should be fixed.
Yeah.
How can that be modified? And saying that it is detected now and later on I will classify that as a non-detection.
Yeah. So the signal to noise ratio doesn't change, it's fixed. The chi-square doesn't change, but this is a cumulative thing. Like this, you are just collecting noise triggers, and you're seeing where this green circle lies in the background of these noise triggers. And based on that, you calculate the significance. So the SNR and chi-square remain same, but the background changes.
You mean you are collecting more and more
Yeah.
data, the
Yeah.
background is
Yeah. So I'll show an example for this, then this will be very clear. So this was on August 13th. One trigger was detected at high confidence, and the chirp mass was around 50 solar mass. Only GSTLR detected it because most other pipelines don't send out high mass triggers if we only have one LIGO detector operational, because like Virgo is not that sensitive, and sending out single detections using just one LIGO detector, then there can be possible retractions. But this was detected at high significance using GSTLR, and all other pipelines also had this trigger in their database. They didn't calculate significance at that time. And as I mentioned, only LIGO Livingston and Virgo was operational. So it would be good if Hanford was operational, because if Hanford was operational, then both these detectors are very sensitive, and then that would have been much easier to detect. But with Livingston and Virgo, this was a trigger at high confidence. What happened on November 23rd is there was a similar trigger, S241123CL, which was detected by both LIGO detectors with an SNR of 19 in Livingston and 2 in Hanford. Now, as soon as you have something like 19 in Livingston and 2 in Hanford, this is most likely a glitch. And the false alarm rate of this trigger was 611 per year. And as soon as you get a detection like S241123CL, like get a trigger, I mean, the significance of S240813D drops drastically. So if you want to take a look at the noise background, so this was S240813D when it was detected. This is right before S24 1123 CL. This trigger was still very significant. S24 1123 comes and fills this region, and then this is the background at the end of the run, and that's why S240813D becomes insignificant. Now, the interesting thing here is, since this was a special event, we did a lot of follow-up studies. If you just manually remove this trigger S241123, then again, this event becomes super significant, but then that's the very definition of biasing your data. Like, you can't look at your results and then remove data. The only way we can remove data is we have a detector characterization team, and if they say that, okay, don't use these times because these times are very bad, and they have independent tools to monitor it, they are not doing match filtering, then we can remove that part of the data. But just looking at the results. But this was interesting. If Hanford was operational, then we would have known for sure if this is a signal or noise. But given the procedure that we have, this is consistent with noise, and most other I think all other pipelines detect this as consistent as noise. Like, this was probably a glitch in Livingston, which we can't actually know for sure. So this is another important plot that most detection pipeline people do just to ensure that your pipeline is working correctly. I'll just explain this plot a bit. So on the horizontal axis, we have the inverse false alarm rate. So let's take this number 10 to the power 6. So if you go up, so what this means is the false alarm rate is 1 by 10 to the power 6, or if you observe for 10 to the power 6 seconds, then you will get one false alarm. Now, this was around this was O4B, which was around 9 months long. So if you calculate how many false alarms you will get at an inverse false alarm rate of 10 to the power 6, like, this is, you can just a simple unitary method, then this should be around 20. That's where the noise curve is. And if you look at, this is the expected curve, and then you can plot this 1 sigma, 2 sigma, and 3 sigma bands from Poisson uncertainties. And this is what we observed. So at low inverse false alarm rates or high false alarm rates, then this dashed line and the white line just overlap. That means we are primarily just dominated by noise, and from here we are starting to get detections depending on what sigma you want to classify as detections. That's equivalent to saying that, okay, at what false alarm rate you will say that it's a confident detection. But this is one, like, this is probably the most important plot that we make as detection pipeline people. And if these two lines don't match here, then that's a big red flag, like something is going wrong. Okay, so I briefly described the GSTLR low latency analysis. Low latency just means near real time, where you're just getting the data and saying that, okay, is this a real signal or not? And the main motivation for doing low latency analysis is multi-messenger astronomy, because you want to send it out as soon as possible. But then the question is, why do we need a higher latency analysis? Or do we need a higher latency analysis? And for the higher latency analysis, as SS sir pointed out, the SNRs and the chi-squares don't change. So we don't need to filter again. But whatever trigger we have, we re-rank those triggers using the updated background, and we get updated values of false alarm rates, which are more accurate. So we re-rank the low latency triggers after the end of the run. And there are some other reasons why we do a higher latency analysis. So when we're doing things in real time, due to issues, this can be some cluster issue, this can be some internet issue, we drop around 5 to 10% of the data, like we couldn't process it in real time. So we refilter those dropped data. We also filter using a higher mass template bank, the gray region that I showed in in the template bank plot a while back. We refilter that region. We don't filter that in real time. And this is also the time to fix any errors if we had something in the online analysis. So primarily for this 4 reasons, we do an higher latency analysis. Do we need an higher latency analysis as our detection rates go up? That's a different discussion, but presently we do have an higher latency, or often this is termed as an offline run. And yeah, we use these runs to decide what triggers to keep in our catalogs. So this is the false alarm rate offline versus online. As you can see, they're pretty much on the diagonal with some scatter as expected. So this actually shows that we are actually doing a pretty good job online. There are some things which shift, and yeah, but it's not that we are doing something very wrong. No, this is Shomi Kodhikari. He's a grad student in Penn State. He also just graduated. Yeah. I think Rana Kodhikari, I think, writes with a K.
Everyone writes with a K.
Okay, so this is just one slide. I'll describe this is so what we do after detection. So the goal of a detection pipeline is to identify that, okay, in this set of data, we have a signal at this confidence. Now, when you know that there is a signal in this set of data, we do a more fine Bayesian search. So we just sample different waveforms and see which waveform fits the data the best, and this usually has around 16 to 21 parameters instead of the 3-parameter coarse-grained template bank that we use. And this is a schematic that we do. Like we just generate several templates and see which is the best match, or the difference between the template and this blue line should be consistent with Gaussian noise, because we have it's expected when we have a detection, then everything is Gaussian around that. Okay, so fine. Now I'll be talking about why do we detect these sources. So at the beginning, I said that, okay, we can detect binary neutron stars and binary black holes. And I also mentioned, like, if you think about the Salpeter mass function, you would expect more binary neutron stars. So the question is, why have we seen so many binary black holes? So if you haven't seen this plot, so these are all the binary black holes, binary neutron stars, and the neutron star black holes that we have detected so far. And this is GWTC5. On the vertical axis, we have solar masses. The horizontal axis doesn't mean anything. It's just organized so that this plot looks nice. But the takeaway message from this plot is, okay, we have very few neutron stars. GW170817 happened 9 years before. It has been 9 years since GW170817, and that's the only compact binary coalescence that we observed that has multi-messenger counterparts. We also detected another binary neutron star, I think in 03, but that was very far away. We didn't have any multi-messenger follow-up, and a couple of neutron star black holes, but nothing like that in 04. But we see a lot of crowding in this region, in this 20 to 50 solar masses. And this is, if you just think in terms of mass functions or initial mass functions, it's a bit unexpected. So the question is, why do we see so many of these sources? And to do this, we need to look at simulated signals. Like we need to put simulated signals in the data and run our search pipelines and see what we are detecting. And doing this is very important. Like let's say now we detect one binary black hole every 3 days. In O1, this was, let's say, one binary black hole every 2 months. But this doesn't mean that, okay, like more binary black holes are merging today than 10 years ago. It's just our detectors and our search methods have become more and more sensitive. And to calculate stuff like astrophysical rate, we need to understand exactly what we can detect and what we don't. So we just simulate some signals, and these signals are drawn from some distributions expected from the, I think this is a GWTC3 like distribution. So distributions expected from the end of the third observing run. And then we run our search pipelines. So a darker shade means there are more events here. So if you look at the simulated signals that were injected, we have a lot of low mass events. But when we run our search pipelines, there is a clumping in this region between 10 and 100 solar masses. And what this tells is, okay, this region is easier to detect, because if it's more massive, then what happens is the signal to noise ratio increases.
Because you have a 45-degree slope is because you have the ratio to be 1. That's what you call primary and secondary. Is that the reason that?
Yeah, so primary is M1, the heavier mass, and this is the lighter. Yeah, because if it's heavier, then it's M1, so there can't be anything here. So that's just the definition. But what happens is, even if we had a clustering in this region, after detection, we have a clustering in 10 to 100 solar masses. What it means is this region is just easier to detect. And we can also take a look at one-dimensional histograms. So the blue one is the injected line or simulated signals that were in the data before doing any analysis, and there were more low mass events, but the orange line, you see a peak in this region. And this basically says that, okay, we are more sensitive in this region, and we have to use these curves to calculate our astrophysical rates and stuff like that. So this is some other interesting stuff that we found when doing these injections. So what we can do is, let's say we do a histogram of the times when we observe these injections, and we saw that that is periodic, like there is, and you can do a folded histogram. By a folded histogram, what you mean is, okay, let's take this day and then just add it, then just keep on adding different days. So just doing it in multiple of 24 hours. And this is in UTC. So we are the most sensitive at around 6 UTC. So this is midnight at Livingston. So then, like, the reason why we think this happens is at midnight, then people don't work on the detectors and there is low human activity. So we have the most detections. Then in the morning, in United States, it's actually the least sensitive because there is more noise and more activities. Yeah. Like if Virgo was more sensitive and if we have LIGO India, this is expected to change, because then this should balance out. But this is very, like, this curve just follows days and nights in the United States. And you can also do a Fourier transform. Then we see a very sharp peak in 1 Julian day. It's not a side, it's not the red one, it's the blue one. And this basically suggests, like, since it's a Julian day, it suggests that this is probably due to human activity. We don't exactly understand why we get these peaks right after one day. Like, this is still, I don't think there's a very good interpretation to this, but this is something that we get in the data. And then there is a peak in 1 week because we shut down detectors every Tuesday for maintenance, and that gives this peak. There are monthly peaks because detector sensitivity changes and stuff like that. So this is something interesting that we get while analyzing injections. I just thought of putting it in here. Yeah. Okay, so these are the O4A sensitivities, and what these numbers in these circles mean, it's just the product of the volume and the time. So let's say For the first sensitivity plot, I showed it was in megaparsec. So this was how far you can see. How far you can see. Now, if you know how far you can see, you can calculate a volume. That's just 4/3 pi d cube. Like you need to correct for cosmology and stuff, but order of magnitude, it's 4/3 pi d cube, and you multiply with that time. So for every value of mass, so primary masses or the heavier masses in the horizontal axis and the secondary masses on the vertical axis, this is how far we can see in volume and time. And the higher value means we can see better. So if you look for binary neutron stars, the value is for GS stellar, it's 0.0071. Whereas for something around 35 solar masses or 60 solar masses is 10 or 18. And what this says is, okay, we do a very poor job while detecting neutron stars. And that's why we detect so few neutron stars. Now, this is another important calculation to do if we want to decide that, okay, do we want to keep this detector for sensitivity estimates or not? So let's say we add Virgo here, what we did in O4b. So Virgo has a, like the farthest Virgo can see for a binary neutron star merger is around 1.4 solar mass. So you can exactly calculate how this sensitivity will change in O4b. So if you have the volume in O4a, you just multiply that by 4/3 pi 40 megaparsec cubed times 9 months divided by these numbers in O4a. And if you just do this, you will see a factor of 1.3 improvement. So adding Virgo for calculating sensitivities gives you a 1.3 improvement in VTs. And definitely we can confirm this doing using simulations, and we did that. But like just doing a back of the envelope calculation, we can justify this factor of 1.3, and this comes due to Virgo.
More answer to this in estimating the Dyson parameters like mass retrieval.
So
These two are two different directions that exist in Pisces or particular NDT.
Yeah.
Then which one is more uncertainty in the parameter.
So these detection pipelines send out a mass. That's the mass of the template. Now the issue is while doing parameter estimation, that's completely different. So from detection pipeline, you can say that, okay, these templates were like GS stellar, let's say, detects this using this template, PyCBC detects this using this template. But then the only thing that you can actually trust is the chart mass, because the M1, M2 can be very different between detectors. While doing parameter estimation, you just take that chunk of the data and start everything from scratch. So
Different channels, which gives us a more accurate
like what I'm trying to say is that none of the parameters are super accurate, because for that we do parameter estimation. Now, which one you trust more, like that depends on the person, like who is using them. But yeah, both have their problems, because it's just a template bank, and it can happen that, okay, some template, let's say 30 solar mass template has the highest significance, but in reality it's just 150 solar mass and 120 solar mass. That frequently happens. And that actually has to do because noise is, again, not exactly Gaussian. So you can just shift and stuff like that can happen. So GSTRL doesn't identify that, it just characterizes the noise background. And if you have a stable noise background, then you can say that, okay, if it's a glitch, you expect that to be right on top of the noise, because a glitch will happen again and again, and that part of the noise background will be filled up. If it's a very rare glitch, then, well, there's not much you can do. And the detector characterizing team has some other tools to identify glitches, and they sometimes send out that, okay, they send out vetoes, like don't analyze this times or don't use this times for calculating the background. And that's what we do. Okay, any other question? Okay. Yeah.
Can I start with that?
Now is also fine.
It's similar to a question, which is, I understand you can't exactly trust one pipeline over the other, or like there are degeneracies. So are there studies like that if these pipelines are biased towards certain parameter areas, like for example, one pipeline will preferentially pick up certain signals more than the other pipeline or something like that? Or are the signals that you're picking up are being uniformly picked up by all the pipelines and being detected by all the pipelines?
No, that's so to answer your question, that's exactly why we have these plots. So if you look at this CWB BBH, this is only sensitive to binary black holes. So if you look at this number, so it's sensitive to around black holes in this region. And this is not a match filtering based pipeline. This is just looks at the data from two different detectors and see if there is any power overlap or not. Now, if you look at match filtering pipelines, you will see GSTLR is more sensitive than PyCBC at this high mass region, because for GSTLR, we have an specialized high mass template bank. So these numbers actually say that, okay, in which region, which pipeline is most sensitive. And based on what you detect from each pipeline, you normalize them using these numbers and then get the rates of astrophysical figures and stuff like that.
Second part of the question. So it is homogeneous across all the detectors. So like it is so same pipeline will detect the same features in Gorgo and Kagra similarly, or different?
Like, you mean, is the signal exactly the same in two
Right.
detectors? It's almost the same, not exactly the same, because there is a geographical distance between the detectors. So it will arrive at a slightly later time with a slightly different phase. But the intrinsic properties, like the masses and spins, should be exactly the same. And that actually goes in, like, for the signal model you had that time for delta t, delta phi, that's a signal consistency check. Like, okay, does this make sense or not? Okay. So moving on, how much time I have left? Okay. Okay.
5 to 10 minutes.
Okay, sounds
10
good.
minutes. 9 minutes.
So this is the gravitation wave, like this is the population that we have using compact binary coalescences, and I actually do not calculate these curves nor work on this, but I just thought of putting it in for completeness. We have two peaks, one around 10 solar mass and one around, I think, 30 to 50 solar mass, and then it's modeled by a broken power law. That's the default BBH model. And there are some weakly modeled things like pixel pop or binned Gaussian process, which Anurjada discussed, I think, a couple of years back, which don't, yeah, last year, where they don't do any strong modeling. This is correct. This is after, yeah. Okay, quickly I'll talk about some detections from O4. This is the heaviest black hole merger that we have detected. And so since this is very heavy, the waveform is very short, and that's why it's very hard to detect, because like this heavy black holes merge around 60 to 80 in this region, like this very low frequency region. And the inspiral part is outside LIGO's band. Like if you have a detector in the decihertz range, then you can see the inspirals. This is interesting because the masses, at least, like, you expect them to be in the mass gap, like from stellar collapse simulations, you don't expect black holes like this, and they're very rapidly spinning. So there are several explanations why this happens. There are some explanations why these are not at all black holes, but if you believe that they are actually black holes, then this is the most probable hypothesis, that they were formed by the merger of two other black holes. Like you can say that, okay, they are like Grava stars or cosmic strings. Like there is a host of papers here if you like, yeah. Yeah, like this is like, if you believe they are black holes, probably this was just formed due to hierarchical mergers. Yeah, like as shown in this cartoon. I am not like, usually when you have hierarchical mergers, they are in clusters, but I am not very aware about formation channels to exactly answer your question. Sorry for that. Yeah. And also it's very rapidly spinning. You won't expect these spins if they were formed through any isolated channel. So this is GW230814. I didn't work in this science case study team, but I just wanted to put in because it's a very clean detection, and clean detections are also very problematic because if you look into something very closely, you find weird stuff. So this is 42 solar mass. The problem is, if you look at the signal and what you should, how the waveform looks like and the observed signal, it appears that the post-merger region decays faster than what's predicted by general relativity. Now, this doesn't mean that general relativity is incorrect, like 1,000 things can go wrong. And people did a lot of simulations, like let's say you inject signals into zero noise using numerical relativity, and then you run the pipeline, standard parameter estimation pipelines with this. So in a surrogate is a surrogate waveform, this is an effective one-body waveform, and you see this systematic deviation. So this can very well be due to waveform systematics, can be non-Gaussian noise, but this is interesting. Since this is very loud, we just saw that, okay, whatever signal that we're getting, like whatever template that we're getting from parameter estimation, that actually doesn't match with the data. Like the data is clearly a bit different. And as we have more and more sensitive detectors, this is a problem because then your waveforms also need to keep up. There might be just environment effects and stuff like that, which are very hard to model. Like something at SNR 10 or 20 is much, much easier to model and detect.
So this
42. And this was also single detector, but yeah. Like the present interpretation is it is just waveform systematics or non-Gaussian noise. Like, so this is a pair of rapidly spinning black holes, and I kept this because if you look at all black holes in GWTC4, there is not even one black hole where the spin of the primary object is in the direction opposite to the orbital angular momentum. And we expect that because there is, like, if you look at the posteriors in this region, but this was the first detection, like that's why this is interesting. And this is again a very well measured detection, like the spin is very well measured. And regarding formation channels, we again expect this to be hierarchical mergers, especially for the heavier one, because again, if it's in isolated channel, then the spin of the black hole should be in the direction of the orbital angular momentum, unless and until there has been any collision or stuff like that. Okay, so that's, it's not that much. Eccentricities are pretty small. Yeah. But again, the issue is that if you put some priors that they're highly eccentric, and then you can do some parameter estimation, like this system you can't observe in LISA, like it will be at the very bottom of the LISA noise because yeah, this is 20 solar masses. So yeah, the previous one a bit, yeah. It's more in the decihertz region, like right after LISA, yeah. Okay, so I'll end by talking a bit about future missions. I was trying to get a better plot, but sorry, I couldn't get. But this is what we have LIGO, Virgo, Kagra. We are in the noise dominated regime, like there is more noise than data. And then if you go to Einstein telescope and Cosmic Explorer, then like Einstein telescope and Cosmic Explorer can actually roughly measure all compact binary coalescences in this mass range. Then you have DESIGO, Big Bang observatories, the plant detectors. India also has one plant detector in this regime. It's called Indigo D. And then you have LISA, and all these are space-based detectors because this is the limit for ground-based detectors due to seismic noise. This is the limit for space-based detectors because like this is due to solar flares and stuff like that. You can't go below 10 to the power minus 4 hertz. And then you have pulsar timing arrays, or if you go to lower frequencies, you have the CMB. And yeah, that's how we can detect gravitational waves in this regime. So just to conclude, like so far match filtering is one of the most powerful ways to detect modeled gravitational waves, and we have 390 confident detections so far. O4 is dominated by black hole mergers, and this is just because they are more easier to detect. And then next generation observatories will be more sensitive and operate in different frequency bands, like observatories like LISA, they'll be operational in the next 10 years, and then Cosmic Explorer and Einstein Telescope. And yeah, so that's all. Thank you again for inviting me. And also this is overall the GSTLAL. And so we no longer have GSTLAL because we are retiring it. So it's now called SGNL. So these are the people who worked for having these results. But thank you.
Okay, questions?
Okay, I have two questions. First, the first one that, so can you go to one of the detections where there was a Livingstone and the Hanford one back? And I could see that the signal itself looked little different. I mean, go back. There were two back-to-back shown. Yeah, I think this one, yes. So if I look at this, is it the same time axis in the x-axis? Because at the x-axis have the same time scales?
Yeah, but the time is slightly shifted, right, between Livingston and Hanford.
Yes, it could be slightly shifted.
Yeah.
I do see differences between the signal.
So like you mean these lines?
Yes, or if I go to the waveforms. See there I see a deep where therefore there is a maxima and there is a minima here.
So you mean there is something like this here and we don't have that dip? Yeah, so that is most likely due to noise, because if you look at the waveform model, there shouldn't be any peak like this here and here. So these are just probably some noise in Hanford at that time. In Livingston, we don't have these fluctuations. Like the blue one is the fitted model. So that is similar, yeah.
That I see in Livingstone, right near the end. There it looks like a
drop. So this one?
Yeah, that's peak, the peak.
This thing?
Yeah.
Oh yeah, here this is after this is noise because it's after the signal. Yeah, so this is the part that is contributing to the signal to noise ratio. And there are some perturbations in Hanford. It's just, it's just again noise. So again, if you have noise like this, you will have these random fluctuations.
So, well, thank you. It was a nice talk. So, I'm curious about how these templates are made. I mean, are there any theoretical background, or these are motivated by some previous data?
So for GSTLAL low mass, we use something called Taylor F2. So they are just post-Newtonian waveforms. Because for binary neutron stars, things are dominated by the inspiral. For higher masses, we use, I think, IMR phenom D. So that's a phenomenological waveform. So they are calculated from post-Newtonian theory, black hole perturbation theory, and numerical relativity. So they are hybrid waveforms. And so these waveforms are there, we just decide what